Hello students, in this lecture we will talk about some results based on connectedness in set of real numbers. So our first result is a subspace of real line is connected if and only if it is an interval. So for the proof, if we take X as a subspace of real line, then first we will prove that if it is connected, then this is an interval. So for the proof, let X be a connected subspace of real line R, then we will prove that X is an interval. So we will prove it by contradiction method. So if possible, suppose X is not an interval, now if it is not an interval, then there exist 3 points x, y, z such that x less than y less than z and x and z belongs to x but y will not be in x. So this will hold in the if x is not an interval, but it is not true in the interval. So if we take a and b interval here, and if we take any 2 points from this interval x, z, then all the points between x and z also belongs to AB. So if we take any y here, so this also belongs to AB. Now here y is not in x, so but y is a real number here. So we know that if we take any interval minus infinity to y and y to infinity, so these are open intervals. So these are open in real line. So as X is a subspace of R, then if we take intersection of these open sets in R with X, then we will get open sets in X. So then minus infinity y intersection with X and y infinity interval intersection with X. So these are open in X. Now if we take union of these two open sets in X, so let us take union minus infinity y open interval intersection with X, union with y to infinity intersection with X. So this is minus infinity to y union with y to infinity intersection with X. So it is a real line except y and its intersection with X, and this intersection is X because y is not in X. So X is a subspace of R here, but R is not containing y here. So if we take intersection of X, then it is X only. Now if we take intersection of these two open sets, then it is minus infinity y intersection with X intersection with y to infinity intersection with X. Then it is minus infinity y intersection with y to infinity. So these are disjoint. So it is y intersection with X only, and it is 5. So now X can be written as a two open sets in X which are disjoint, and these are non-empty also. Also, because of this, if x less than y less than z and x and z both are in X, so if we take X element, it is in minus infinity to y intersection with X, so it is non-empty, and Z also belongs to other open interval, so it is also non-empty. So X can be written as a union of two open sets which are non-empty and disjoint. So this implies that set X is disconnected. But it is not true that it is given that X is a connected subspace of real line. So it is a contradiction. So our supposition is wrong, that we have taken X is not an interval. So X must be an interval if it is connected subspace of R. So X is an interval. Now we will prove the converse part. So if we take X is an interval, then it will be connected. So for the converse part, we take let X be an interval, then we will prove that X is connected. So again we will use a method here. So if possible, let X is not connected, means X is disconnected. So from the definition of disconnected space, then there exist two disjoint, non-empty open sets, that is A and B in X, such that X can be written as A union B, and these are disjoint. Now X is a union of A and B, so let us take a point A which belongs to A and B point which belongs to B. So if A is in A, B is in B, and these are disjoint sets, so we can say that A and B are not, and also say that A is less than B. So we assume that A is less than B here. Now we define two sets here, that is A1, which is intersection of AB interval with A, and another set B1, which is intersection of interval AB with B. Now A1 is a intersection of AB and A, and B1 is a intersection of AB and B. So from here we can write, then AB interval can be written as a A1 union B1, because it is given that X is an interval. So if X is an interval and X is a union of A and B here, so if we divide this interval into two parts, A and B, then A point is here and B point is here. So we have taken intersection of this AB interval with A and B. So this part is A1 and this part is B1. So if we take union of both, then it is AB interval only. So here we can write it is a disconnected set with disconnection A1 and B1. So it is a disconnected with disconnection A1 and B1, because here A1 and B1 are two disjoint which are non-empty also, because A1 is containing at least A point and B1 is containing at least B point here. So it is non-empty closed sets in interval AB, because it is a closed interval. So AB can be written as a union of A1 and B1. So it is disconnected set with the disconnection A1 and B1 here. Now further, if we take that Y is a supremum of set A1, and here A1 is a intersection of closed interval AB and A. Now if A is a supremum of A1, which implies that Y belongs to A1 closure. Now A1 and B1 both are disconnection of AB interval here, so these are separated sets. So if Y is in A1 closure, then Y does not belongs to B1, because A1 and B1 both are separated sets, so A1 closure intersection with B1 is empty. And also if we take an element which is greater than Y but less than equal to B, then X does not belongs to A1, because we have already taken supremum of A1 is Y. So if there is any element which is greater than that Y, then it will not be in A1, otherwise it will be the supremum of A1. So because of supremum of A1 is Y only, and this implies that if we take an interval which is a semi-open interval, open with X and closed with B, which is containing B1, because it is a part of B1 here, so which implies Y belongs to B1 closure, because here Y is not in B1, and if we take any number greater than that Y, then it is not in A1, so Y belongs to B1 closure here, and which implies that Y does not belongs to A1, because these are separated sets. So also A1 intersection with B1 closure is empty. So from this we can write Y does not belongs to A1 union B1, because Y is not in A1 and Y is not in B1 also. So which implies Y does not belongs to AB interval. But it is not true that we have taken Y is a supremum of A1. So it is an intersection of closed interval AB and A. So it is a closed interval, so Y should belong to AB. So it is a contradiction. So our supposition is wrong, that we have taken X is disconnected. So X must be connected if X is an interval in a real line. So our supposition is wrong, that X is disconnected. So it is not true, then X will be connected only. Now in the previous result we have proved that intervals are connected in the real line. So if we take any known interval in the real line, that will be disconnected. So it means only intervals are connected in the real line. So for the proof of it, let E be any set which is not an interval, so that we take any 2 points from E Let us take AB. So if it is not an interval, then there exists a point C such that A less than C less than B and C does not belongs to E. So now let us take two open sets minus infinity to C and C to infinity. So which are open in real line, and E is a subspace of R. So it is a known interval subspace. Then if we take intersection of these two open sets in R with E, so it is minus infinity C intersection with E and C infinity intersection with E. So these are open in E. Now it is a open set in E. So we can write minus infinity to C intersection with A, which is contained in E, and it is a proper subset of E. So is a proper because there is an element in E, that is B, which is not in this set. So it is a proper subset of E. And also if we take this set minus infinity to C interval intersection with E, so it can be written as minus infinity to C. So it is closed with C intersection with E because C is not in E. So if we take intersection of E with this open interval and with this closed interval, so that will be same because C does not belongs to E here. So these are equal. So this is a closed set and this is open. So from here we can say that minus infinity to C intersection with E is a closed set. In E. So which implies this set is both open as well as closed. So if a set which contains a proper subset which is both open and closed, then we have already done one result, that set is disconnected set. So this is disconnected. So we have proved that if it is not an interval, then it will be disconnected set. So further we have one corollary, that real line is connected. So real line is given by minus infinity to infinity. So it is a interval here. So intervals are connected. So this is also connected. Or we can say that set of real numbers with the usual topology is connected. So if we take set of real numbers with this topology, that is connected. Because in the usual topology, we generally take a open intervals. So it is connected. So from the previous result, we can easily say that connectedness is not a additive property. It means subspace of connected space need not be connected. So we can prove it by taking one counter example. So let us take one counter example of it. So for this, let R be the set of real numbers. And we take topology on it, that is usual topology. on the set of real numbers, then we know that this space, set of real numbers with the usual topology, is connected space. So it is connected, and if we take set of rational number represented by Q, so let Q be the set of rational number and we know that Q is a subspace of R, then we will show that this set of rational number is not connected. So if we take any real number, such that R does not belongs to Q, so it means R is a irrational number. Now if we take minus infinity to R and R to infinity, so these are open intervals in R, so these are open sets in set of real numbers with the usual topology. As Q is a subspace of real numbers, then if we take minus infinity R intersection with Q and other interval intersection with Q, so these are open in Q also. Now take union of these two open sets in Q, so minus infinity to R intersection with Q, so it is minus infinity to R union with R to infinity, then intersection with Q. So it is set of real numbers except R point, then intersection with Q. So R is not in Q, then this intersection is Q only. Now if we take intersection of these two open sets, that is minus infinity R intersection with Q, then intersection of R to infinity, then it is minus infinity to R intersection with R to infinity. So these are two disjoint interval, its intersection with Q, so it is phi, and these two open sets are non-empty also, so Q can be written as a two disjoint non-empty open sets, so it means Q is disconnected. Now it is a set of rational number, that is a subspace of set of real numbers which is connected, but set of rational number is disconnected. So we can say that connectedness is not a additive property. So now we will prove intermediate value theorem of calculus. That is, let f be a continuous function with f from closed interval ab to set of real numbers, and if we take any number r which is a real number between f of a and f of b, then there exists a number c in ab such that f of c is equal to r. So for the proof, and we have given a set AB here which is an interval, so since AB is an interval, then it is connected because every interval is connected. So, and it is also given that function is a continuous here. So f is continuous, and it is continuous from closed interval ab to set of real numbers. And we know that continuous image of connected space is connected. So if ab is connected, then f of ab is also connected. And it is connected in set of real numbers. And from the previous result we can say that subspace of a real number is connected if and only if it is an interval. So which implies f of ab is an interval. So which implies that f of a and f of b both are real number such that f of a is less than f of b. Because it is an interval, so we can write it here. Now it is given that r is any real number between f of a and f of b. So if r lies between f of a and f of b, such that f of a less than r less than f of b. Because f of ab is an interval here, so we can write it here. And also f is continuous function. Since f is continuous, then there exists c in ab such that this r number which lies between f of a and f of b will look like as f of c. So this proves the result. So now we will do generalization of intermediate value theorem. And for this, first we need a definition of total order. A total order is a relation on a set that satisfies these properties. And first one is a reflexive property, and it is if R is a relation, then X related to X only. And transitive, so transitive means if X is related to Y and Y is related to Z, then it implies X is related to Z. So it is transitivity. Now the third property, if it is an anti-symmetric property, if X is related to Y and Y is related to X, so which implies that X is equal to Y. And fourth one is a comparability, that is also known as trichotomy law. So either X is related to Y or Y is related to X. So only one will be true here. So if we take any set X with this relation less than equal to, then it is a total ordered. So this relation is a total order here because X is less than equal to X here, so it satisfies the reflexive property. Transitivity also, because if X is less than equal to Y, Y is less than equal to Z, then X is also less than equal to Z. And anti-symmetric also, if X is less than equal to Y and Y is less than equal to X, then X is equal to Y only. And comparability also, so here if X is less than equal to Y, then either this will hold or this will hold. So this is a total order here. Now definition of a totally ordered set. If a relation R on a set satisfy the properties of total order, then X is called totally ordered set. Then this set X is a total order with this relation. So if any set X with any relation satisfy these three properties, then that set will be the partially ordered set. But if we are taking these 4 properties, means 3 properties with the comparability property also, then it is a totally ordered set. Now further we define order topology, and order topology is defined on any totally ordered set. So if we take any set X with the less than equal to relation, and we know that this is a totally ordered set, then order topology on this X is a topology generated by basis B consisting of the union of the sets of the form. So its union will be in the form of these 3. So that is open intervals of the form AB with A less than equal to B in X. So if X has a smallest element A naught, then we can take half open interval closed with A naught and open with B, then which satisfy this A naught is less than equal to B in X. So if X has the largest element B naught, then again we can take half open interval of the form. So it is open with A and closed with B naught, with A less than equal to B naught. So the topology generated by these bases is called the order topology. So now we have some examples. In the first example we have, if we take any set of real numbers with order topology, so in the order topology, if we take any basis in this form, so that will become a open intervals only. So it will contain only open intervals, so that will become usual topology. So now in the next example, if we take positive integer with order topology, so again the order topology will contain all the positive integer because it also satisfies these conditions. So this will gives you a discrete topology. So further we generalize the intermediate value theorem, that is, let f is a continuous function from x to y, and here x is a connected space and y is an ordered set in the order topology. And if we take 2 points of x, that is a and b, and if r is a point of y lying between f of a and f of b, then there exists a point c which is a point of x, thus that f of c is equal to r. So we will prove it by contradiction method. So if we take any 2 points in x and r is a point of y here, such that it lying between f of a and f of b, then if possible let there does not exist any point c in x such that f of c is equal to r. So from here we can say that r is a point of y which lying between f of a and f of b, but it is not in the image of x by f. So it is also given that x is a connected space, and f is a continuous function, and we know that continuous image of connected space is connected. So f of x is also connected here, and f of x is a subspace of y here, so it is connected in y, and y is an ordered set here in the order topology. So if we are taking r is a point of y here, so we can take interval minus infinity to r and r to infinity. So these are open in y, as f of x is a subspace of y, So if we take intersection of f of x with the open sets of y, then minus infinity to r intersection with f of x and r to infinity intersection with f of x. So these are open in f of x. So if we take union of these two open sets, that is minus infinity to r intersection with f of x and union with this interval intersection with f of x. So it is minus infinity to r union with r to infinity intersection with f of x. Now from here we can say that there does not exist any point c which is a point of x, thus that f of c is equal to r. So r is not in the image of x here. So from here we can say that its intersection is f of x, as r does not belongs to f of x. So if we take intersection minus infinity to r intersection of f of x, then it is minus infinity to r intersection with r to infinity and then intersection with f of x. So it is empty because these are disjoint intervals, so it is f of x. So this is also empty, and also these two open sets are non-empty, as minus infinity to r intersection with f of x is containing f of a point, so it is non-empty. And also if we're taking r to infinity intersection with f of x, it is also non-empty, as f of b is in this set. So we have written f of x in the union of two open sets in f of x which are disjoint and non-empty sets here. So from here we can say that f of x is disconnected, but it is not true because f of x is connected in y here, so it is contradiction. So our supposition is wrong, that we have taken there does not exist any c point in x such that f of c is equal to r. So there exists a point c in x such that f of c is equal to r. So this way we have proved the generalization of intermediate value theorem in topological spaces. So in the next lecture we will discuss about the connected components in the topological spaces. Thank you.